This one is probably will have, so this class will have 70% contents will be in this textbook. There's a newer version, but I don't think that's necessary. If you can buy a used one online, I think it's somewhere around 60, 70 bucks or even cheaper, I don't know. The newer ones are $120 or something. It's pretty expensive. It's pretty thick as well. And the second one, this one, CMOS VLSI design. I just realized that a lot of institutions in the US, they are using this one, this textbook for CMOS VLSI courses. It's a really classic VLSI design book. They can see the, so they started with a MIPS CPU design. So these are all the chip layouts. Before introducing any digital blocks, they started with a MIPS CPU. MIPS is one of the computer architectures you are going to learn in this semester if you are taking computer architectures. So MIPS, ARM, RISC-V, all these kind of things. And then they started introducing all these digital blocks. Probably let's look at the table of contents. Show really quickly about what's being covered over here. Okay, then followed by all the CMOS logic, all the gates, layouts, and a simple MIPS processor. You probably are wondering, you haven't learned all these data paths, control circuits, and ALUs in the CPU. How can you start to design a MIPS processor? So you are not designing a MIPS processor in this book. It's actually just give you the RTL code, and you can directly put it into the path frame and connect all the other parts to the CPU and make a chip out of it. This is just for undergraduate teaching course. It's not for a graduate level circuit design or CPU design course. So all the other ones are pretty similar. You can see probably 50% whatever being covered in this book, you can see in this book as well, right? In this one. Okay, that's a good one. Okay, look at this one as well. And there's a website for the book I just mentioned. So for the first one, it's a cmosedu.com. No? Oh, internet connection. Okay, so you can see that's a newer version of the one I just mentioned from Dr. Baker. And this was just launched last year, and Dr. Jeff Jessing contributed one chapter in this book as well for nanofabrication, FinFETs, or all these new technologies being covered. But all the rest of them are they don't have to be updated. Like what you learned from Newton's law is being not changed for so many hundreds of years. And that's another textbook. It's not related to this class. If you are looking at some of the courses, you can go to courses and go to simulation, some of the simulation files, or some tutorials of electric VLSI or cadence. There are a lot of good resources you can find in this website. And for the second textbook, it's called cmosvlsi.edu or .com? .com, I guess. And we go to supplements. Oh, it's already here. Lecture slides. Where are the labs? Oh, the labs are here. Okay. So we are not going to use the electric labs being covered in this website. So you can see the first one is they use the cadence and synopsis for the 4 labs, and the second one is the electric version. Same lab, the electric version. And you can find out the if you download the electric library to your computer, you can actually open that library on your PC, and you can see all the layouts already made in the textbook. You can directly use it, just make all these connections in between all these modules to build a processor. You are not actually designing the CPU. You can still learn something about how to make all the interfaces and data paths for that one. So you are going to follow the lab instructions on my website. You can easily find on my website for the labs for this course, but not these ones. It's good to explore these ones as well. Okay? You can see these are all these main resources you can find online for VLSI design. So that's another one for the second textbook. There's something else I want to show you. So that's a company's website. It's called the Western Design Center. So the CEO was a speaker I invited to the class last semester, Bill Mensch. And he just contacted me a couple days ago, see if I can hire a student to work on to convert RTL, the code, a Verilog code into a chip, into ASIC for his CPU. So he developed this CPU, 6502. There are newer versions right now, but he invented this CPU back in the 70s, and which was used for Apple II computer, I think. And he got a lot of patents on this CPU. I think he's a good teacher because he taught his wife to lay out the entire CPU for him, and that was fabricated in the 80s. He just told his wife like you should. So here's a while I just laid it out, right, and make all the connections, and that's the chip. So his wife was a psychology major and know nothing about circuits, but still laid it out, and that works. But there were some minor issues for the CPU. I think that was he told me. In the 2000, I mean about 10 years or something, 10 years ago, he hired one person who knows IPGAs, and they convert. So that person just converted all the physical circuit into Verilog code, RTLs, register transfer level code, to describe all the behavior of the CPU, which can be directly converted into a chip. But he was not able to convert it into an ASIC, which is application-specific IC. So whatever they did is they just synthesize the Verilog code into the IPGA. So now they are selling a design kit based on IPGA. So it's an IPGA. IPGA is a. You are going to learn a lot of IPGA stuff in embedded devices this semester. So they just download everything to a blank digital logic array, gate array. So they will make, so the synthesized file can make all the connections on the gate array in order to turn that IPGA into a chip, right? So it's not an ASIC, doesn't like the CPU being used in your iPhone or Samsung smartphone, but it's the IPGA. It's still being used, still being sold online. You can find it available online, but the final purpose is they still really want to turn the design into a ASIC. So they're going to send the design to TSMC or Samsung or somewhere else for fabrication. So he was thinking to use a 350 nanometer technology from TSMC for the fabrication. So why is that? Why does he want the chip to be ASIC instead of IPGA being sold? So you have already used all the Arduino chips, the CPU, the little CPU on the board, right? Is that IPGA based or is it ASIC? It's ASIC, it's not IPGA, right? IPGA is something like you can buy an IPGA chip online. It's a square shape, has 400 pins, but only 200 are being used. It has a lot of redundant space on the chip, right? And has billions of transistors. They program it, probably only use the 10% of the space on the IPGA for the chip, right? The cost will be higher because they have to buy the IPGA, the blank IPGA from somewhere, and then burn it to make out that chip. But if ASIC is totally customized, they can fabricate all the chips, all the wires and transistors based on the GDS2 file in the foundry. The cost will be higher if you only fabricate 20. For 350 nanometer technology, I think it's going to be like over $50,000 just for prototype 10 chips or something, 20 chips. But if you fabricate millions of them, you can sell every chip at the cost of only like $1, $2. That's why you can buy the Arduino 328P chips on DigiKey just for $2. Because it's ASIC. If it's IPGA, it's going to be more than $8 for each chip, right? So ASIC is the purpose, is the final goal. We don't have the funding to do this yet, but if some of you guys are interested in that, we can, explore some opportunities. There are two foundries we can fabricate this chip. One is MOSIS, one is eFabless. You can see this company. $70,000, 20 weeks. 100 samples, 100 chips, $70,000. But I don't know what technology this is based on. Probably 180 or something. It's still a lot of money, right? That's why you can see fabricating ASIC is the bar is really high. It doesn't like you are just learning programming on YouTube. You just learn from LeetCode for 2 months, you can get a job, right? Why it's so hard for ASIC designers to be successful? Because it's so expensive. You have to learn it in the college. And there are some really successful stories about using eFabless. So here's one of them, QFlow. This is another project I want some of the students, some of you guys, to work with me to get it worked out. Since this is really interesting, because using all these industry standard the tools like Cadence or Synopsys are super expensive. You cannot afford it. But there are a lot of free software available online, but none of the companies are using them. They are not up to date, or they cannot use the really state-of-the-art technology like 7 nanometer, even 65 nanometer, probably not available for these kids. However, if you are just doing like 130, 180 nanometer technology, I think it's fine. And QFlow is a workflow. It's not a one software. It's a workflow of using all these kinds of different kinds of available freeware online to start from nothing until a full-scale IC or SoC, system on chip. I have, because the author here has done that. So what is this? That's just some drawing by a 3 years old. That's a chip layout. That's a CPU. And if you zoom in, I probably couldn't see that. It's just a high resolution chip. I mean, these are just all the wires and transistors. And the chip was fabricated. You can see it's already soldered on the PCB. And he did some LCD application. And it's like a MCU. It's being used for, or microcontroller being used for this experiment. So which means it works, right? If it's not working, then you cannot see anything on the LCD after programming. It works. And here's the CPU, or SoC. So CPU is over here. So RISC-V, you need to know, RISC-V is really popular right now. It's an open source CPU IP core you can use because it's been dominated by ARM for so long. And every single CPU being developed by any company, if they're using ARM, they have to pay ARM some money. I don't know how much, but they have to pay them. And whenever you are buying an iPhone, some of the money is used to pay ARM, which is a British company. They don't. So whenever they are designing an SoC, system on chip, like this, being used for the smartphone or laptop, they do not have to design the CPU by themselves, right? They just buy the CPU. buy the IP core. They don't need to know what's inside. They just buy it and place it into their chip design, into the layout, and make those connections. But RISC-V is free. That's why it's attracting a lot of attentions. So this project is totally based on free stuff, right? So free software and free CPU core. And I don't know if the SRAM is free. What I heard is a lot of foundries are providing SRAM blocks. So because it's not being changed at all. They're just memory banks, just storage. So static RAM is normally used for cache because it's cache. Cache. No, so cache, C-A-C-H-E, right? So it's a really high-speed memory being placed adjacent to the CPU inside the chip. Doesn't like RAM, DRAM. So DRAM is normally a RAM card you can plug into the motherboard. But SRAM is static RAM is normally used as a cache adjacent to the CPU because it's high speed, higher cost as well. And you can see ADCs, DACs, amplifiers, temperature amplifiers. So normally they need a temperature amplifier. Whenever it's too hot for the CPU, they will shut it down instead of just burn it down, right? And PLL or oscillators. So you can look at what are being included into this SoC. It's like a microcontroller. SPI, right, ring oscillator, band gap is providing a voltage reference for the chip. So all these type of things, a lot of stuff. And this can be difficult, but the thing is, you are not actually designing every single module by yourself. You just use the parts and put them together and make a chip. But you know what? If you can just combine all these blocks and into a chip and make it work and do some verification, great job. I'm pretty sure you can get a job easily in any of the big companies. So if we're just looking at ADCs, which will be covered this week, and we'll do a really quick ADC DAC experiment next week, just ideal versions in simulation. If just for ADCs, there are so many types of ADCs. A lot of people just working on different types of ADCs, and they can graduate from a PhD degree and they just do it for their whole life. So we are going to look into some ADC structures. And I just found out one very interesting project on Columbia University. It's not an undergraduate level experiment, it's a graduate level experiment. You can see the students involved in this experiment are all PhD students, and it's a 1-year project. Definitely, we couldn't do it, but I think this is an ideal, really good project for senior seminars over here in the future. So we look at the IC design, and we are going to look into the details of the this part, and you are going to design a D flip-flop using LT Spice. I think it's due next Friday. Yeah, no worries. We just follow everything, and eventually the IC was laid out by all these students over there, graduate students, and that's the registers. And here's a chip, only one ADC, and that's based on I think 350 nanometer technology from TSMC, I guess. And you can see that all these modules on the chip, and all these are the bonding pads. And that's the entire chip. But you can see here, the one I just showed you, I already turned off that one. But the ADC is only a little tiny part on the CPU, right? Probably you need a different structure or different technology for that. Or maybe just optimize the structure. But you can see all these are wires or memory banks or capacitors. But only these parts are the really functional modules. So the wires are taking a lot of space because they know they are not including any other things on the chip. So that's why they are not saving a lot of space on the chip. That's the entire ADC. Here's the chip fabricated. So they took a picture under the microscope. Okay, this is another project which is really interesting. If you are interested in doing that, we can probably planning on doing this in the summer, this summer, but no funding. We can look for funding. You can apply for the undergraduate research funding for this. All the other fundings available here are based on science, right? You have to discover some new knowledge, not like these old things. They have done this. Why do they want to fund you? But it's really good for students to learn it and get a job, right? So that's why I think I'm willing to do that. All right. So these are some things I want to let you know. So you know that tomorrow we have a lab. If you cannot make it, you can still do it remotely. So do a really quick review because I know a lot of you guys have known this a lot really well. So won't spend too much time on this. I just realized one thing because some of you guys took my logic C241 last semester, but you didn't have circuit one in the past. So this can be challenging. But I have two videos already, two links on the website, course website already provided to you guys. And just click the links, watch the lecture videos, and try to understand what's going on. So this all this circuit series. So the first one, superposition. Why is this important? Because it's being used in a DAC we are going to do next week, tomorrow actually, for the lab. If there's a circuit looks like this, the superposition is the method you can use to solve a circuit. That's VL. V1, R1, R2, B2, R3, B3. So what is VL? Use superposition to get VL. The procedure of using a superposition method to solve a circuit, what's the first step? Yeah, one voltage source at one time and short all the other voltage sources, or disconnect all the other current sources. Okay, let's start with V1. V1 only, then what's going to happen? So the circuit looks like V1 only, R1, R2, short, so short V2. So V2 is gone, only R2 is left here. And that's VL. That's R1. So what is VL? Is that voltage divider? And how it's being divided? Let me know if you have forgot everything about circuit one, okay? Which is understandable. No worries. Yeah, I know. Are they in parallel? Yes, they are, because ground, they are shorted. Even I don't draw it, they are still shorted together, right? Ground is just one common ground on the board, on the circuit. So R2 and R3 are in parallel. So if you can combine these two as one R, which is R2 in parallel with R3, right? So VL is actually the voltage here is a voltage divider, right? It's like this R1, R2 in parallel with R3. This is R1. Here's VL, right? So VL equals to V1 times R2 in parallel with R3, R1 plus R2 in parallel with R3. That's V1 only. And then the next step is just V2 only, and you short these two sources and just get whatever VL is from the contribution V2. Short V1, now V2 only. Is V3 shorted, or you want to keep it here this time? So what is VL this time? So that's VL1, now VL2 from the contribution V2. How to convert this circuit to a form that is familiar to you. Are these resistors in parallel? Right? So because this is from this node, the same node here is the same node, same wire, and through this resistor to the ground, through this resistor to the ground. So these two resistors are in parallel. We can convert this circuit to something like that's R1, that's R3, that's R2. Here's V2. VL is still the voltage drop across R3, so that's why you can still do that. Here's VL. So VL2 equals to V2 times R1 in parallel with R3 over R2 plus R1 in parallel with R3. It's the second one from the contribution of V2 only. And V3 only. V3 only. Short these two resistors and only apply this voltage to the circuit. It looks like this. This will be R1, this will be R2, and this is R3. And V3 only. And V3 goes through R3. So is this still VL? Let me know. Is this still VL? So look at here. VL is the voltage across these two guys. And now, because I'm doing V3 only, so this is shorted, this is shorted. So I have R1, R2 in parallel. That's why I can do this. But now the question is VL still the voltage across these two terminals? And why? Look at it. So VL is the voltage across R3 and the V3, right? And now VL is the voltage across R2 or R1, R2 in parallel. However, if you just look at here, VL is this, the voltages across these two terminals, still same terminal, right? Still same terminal or not? Yes. So this is still VL. Same. R3 V3, R3 V3, no difference. That's still V out. So now V out 3 equals to V3 times, how do you want to do this? These are in parallel. R1 in parallel with R2 over R3 plus R1 in parallel with R2. Right? And then eventually V out is a contribution of all these V outs, right? V out 1, V out 2, V out 3. So just add them together. Which is, that's why it's called superposition. Right? They're being superimposed to each other. VL1 is V1 times R2 in parallel with R3 over R1 plus this guy added to VL2, which is this one, V2 times R1 in parallel with R3, R2 plus R1 in parallel with R3 plus VL3, which is here, V3 times R1, R2, R3 plus R1 in parallel with R2. Let's take an example, plugging the numbers to it. What if R1 equals to 2K, R2 equals to 4K, 2K ohms, 4K ohms, right? R3 equals to 6K ohms, V1 is 2 volts, V2 is 4 volts, V3 is 6 volts. Just plugging. So VL equals to V1, which is 2 volts, times R2 in parallel with R3, R2 in parallel with R3, right? So R2 in parallel with R3 equals to R2, R3, R2 plus R3. I will send you some videos if you are not in circuit 1. This can be hard, but actually, if you have known this, it's easy, right? I will send you some videos. Definitely do it if you didn't learn this in the past. So R2 in parallel with R3 is this guy. Let's just do a quick calculation. R2 in parallel with R3, which is, yeah, just plug in the numbers to save time. Okay, 2.4K over 10K, no, 4.4K. K squared actually, so K times K, because there are two Ks multiplication, right? Just use this equation to calculate for the value of this. So we are just doing this, plugging the numbers, plus 4 volts, which is V2, 4 volts times this part, just do a calculation according to this equation, right? So you're getting 1.5K times K over 5.5K. You can verify it after class. And then V3 is 6 volts. And then R1 in parallel with R2, R3 plus R1 in parallel with R2. Same, use this equation to calculate for these values and put R3 inside as well. So you can eventually get this over 7.3K. So you're getting 1.1 plus 1.1 plus 1.07, and this is something around 3.27 volts. That's the VL you're going to get using the superposition theory. Okay, there are many other ways to calculate VL from this DC circuit. What are the other methods you learned? Mesh current methods, node voltage methods, right? All these kind of things. Superposition is just one of them. Superposition, okay? So eventually you can get V out. And you want to verify this one in LT-SPICE really quick. How to verify it? Writing the code tomorrow. Do not use schematics. Use the code. For such a circuit, how do you code it up? Define all the nodes. This is definitely 0. I name it 1, no problem. 2, 3, still 0. What is this? 4, 2. Just verify if you're still awake. So this is still 2, right? Same node. And do you have another node? Here. 4. So VR equals to V4. Really? VR equals to V2 or V4. V2, right? So here is 2. VL, V2. Okay? Not V4. V4 is here. V4 is this voltage. When I'm talking about V4, I'm meaning V node 4 compared to ground, right? Okay, so let's write the SPICE code. Start from V1. V1 space is the voltage drop from 1 to 0, and it is 2 volts. And then R1 is from 1 to 2, and it is 2K. It's not necessary. You can do that, but it's not required. And then R2 is from 2 to 3, and it is 4K. And V2 is from 3 to 0, and it is 4 volts. R3 is from 2 to 4, and it is 6K, I guess. And V3, which is this guy, is from 4 to 0, it is 6 volts. And do a transient analysis. Dot tran, 1 second, doesn't matter. 1 second, 1 millisecond, 2 seconds, doesn't matter. Just look at the curve, DC voltage in terms of time. It's not going to be changed. And just run this in LT-SPICE. So there are how many ways to run the code in LT-SPICE? How many different ways? How many different ways you can run a code in LT-SPICE? Just to remember that. How many different ways? Yeah, run the code. I think it's 2. What are the third one? So the first one you can run a TXT file. Yeah. The second one you can directly do a .op and put all the SPICE code into LT-SPICE. And that's it. And the third one you can simulate it not using a code. Just use a schematic. Just put the symbols into LT-SPICE and run it, right? So 3 different ways. So let's do the text editor version really quick, and let's verify this. Whatever we just calculated. So start with the text editor. Okay. So keep in mind, if you're using a text editor to put it up, the first line has to be the title. You cannot put any circuit thing in the first line. So it has to be, you just type whatever you want to name it, example 1 or something. And then V1, and it doesn't have to be capitalized V, and it doesn't have to be V1. You can name it whatever you want, but it has to start with V. So SPICE knows it's a voltage. So for resistors, it has to start with R. For capacitors, it has to start with C. Right? That's important. However, it's not important if you're capitalized or how to number it, like V1, V2, Vx, whatever. Doesn't matter. It has to be V. Start with V. So let's say V1 is start with a 0, node 1. So the voltage drop is from node 1 to node 0, which is ground. And the voltage is 2 DC volts. And you can also do DC and 2, but you don't have to specify that. If you just directly put a 2 there, it's DC 2 volts by default. Or you can just do 2 volts. It's just not necessary. I will just ignore it. Just do a V1 from 1 to 0 and it's 2 volts. And then R1, it can be R1, smaller case R1, doesn't matter, but has to start with R. Let's just do R1. It's from 1 to 2 nodes, right? And then it's 2K. And then R2 from 2 to 3, and that's a 4K. And then V2 is from 3 to 0, and that's 4 volts. And R3 is from 2 to 4, and that's 6K ohms. And then V3 is from node 4 to node 0, and that's a 6 volts. And then do a transient analysis for 1 second. It can be 2 seconds, doesn't matter. We just want to see a DC voltage. So that's the entire spice code for the circuit. It's just creating a net list for all the connections of the circuit. And now let's turn it off and start LT Spice. So open it from the desktop. So it's not showing up here because you have to do it all files to show it up. So just open this TXT file in LT Spice and directly run it since it's ready. So you can notice that the first line is a title. It's a different color, so it's a title. If you delete that line, then your first circuit line will become the title, and you'll lose that first voltage. So you need a title over here when you are using a text editor. So run it. So I want to add a trace, right? So right-click the plot pane and add a trace. So which voltage you want to look at? V2, right? So V2 is V out. 3.27 volts. Is that what we calculated? So here, the calculation is verified by the LT Spice. So that's how you do it. That's the superposition. So another thing important, for this circuit, you can convert it into equivalent circuit first, which is the simplified version. And then you do the calculation. You can still calculate the VL, but in the easier way. And you have to use superposition and the 7-use equivalent in tomorrow's lab. Let's do this really quick. That's the first example, and then we can do the second. If you have forgot whatever is this, right? So just go to the website. I have 2 videos. One covers the superposition, one covers 7-use equivalent, and another one covers LT Spice, how to code up LT Spice code, right? For circuit analysis. So for this one, the same circuit. What's the equivalent circuit of this one? Has multiple voltages converted into an equivalent circuit. How do you do that? So see, we have to do so many calculations, right? For this simple DC circuit. If you convert it into the 7-use equivalent circuit, then you can have a have a simplified version of the circuit and just directly run it. So know what VR will be. What are the 2 steps? The first step, get RTH. Because all the 7-use equivalent looks like this, right? Here's VL. Here's RTH. That's the equivalent resistance. And here's the ETH. That's the equivalent voltage source. So all the DC circuit can be converted into this version. So now we are just trying to convert this guy to this. So we need to calculate RTH and ETH. So RTH is need to short all the DC sources or disconnect the current sources. So let's just short everything and keep the resistors there. Ground, ground, ground. So here's VL, that's the output, and R1, R2, R3. So you have to look backwards to get an equivalent resistance. Just look in that direction. So look in that direction, which means you are imagine you are injecting a little current from here, injecting a little current from here. So the current is going to flow in this way. So the first branch start from here. That's the first current branch. And then this entire thing is in parallel with R3. However, there are another two sub branches. The equivalent circuit equals to R3 in parallel with R1 in parallel with R2. So whatever here in parallel with R3 will be the equivalent resistance. Just look backwards, right? So that's RTH. So what about ETH? ETH. How to calculate ETH? You don't have a load. So imagine you have a load, right? So the first is RL, that's a load resistor, whatever is the device being driven by this circuit. So you need to remove the load first and then look at what's the voltage here. So that will be the ETH. But you have to keep all the sources in the circuit, like voltage sources have to be kept in the circuit because you have to calculate all the contributions to the output voltage. So what is VL? We just calculate it from the superposition method. So whenever you are doing this, you don't have to use superposition. And you can use whatever you want, like a match current method or whatever. Just calculate VL, and VL will be ETH, right? Eventually, you can convert this circuit into this. No, VL and ETH, RTH. This is actually ETH. And ETH in this open output circuit is exactly VL. I know this is confusing, right? So why VL is being used over here for the input? Because I didn't put a load here. So the original circuit doesn't have a load. If there's a load, VL will not be this VL. You know what I mean? If I have a load here, what is the voltage here? Is that still the same VL as this one? No, because this resistor has a voltage drop across this RL. It's going to be a totally different circuit. Okay. Yeah, no worries. I mean, if all this circuit one stuff, you can still go back to. I'm going to send everybody all the videos. Just watch the videos and give you some assignments to work on. This can be easy. But you must know this in order to do the lab tomorrow. And another thing I want to let you know, and if you feel like you didn't learn all this circuit one stuff in the past, don't be nervous because you don't have to use this. We're not using this a lot in the rest of the semester. It's only lab 2 actually. So for all the other ones, probably we're going to use the body dividers or something like that, but not all these complicated, all these advanced circuit analysis series will not be used. We're just going to do the transistors and do the current analysis and just lay out the chip. That's the purpose. Okay. Any questions? Anything? Yeah, 0.5 works. Yeah, one more thing. We have 1 minute left. So you need to know the pulse function. what are inside? What are the arguments inside this function LT_spice? So there are several parameters, right? So the first one is low voltage. So the parameters, right, in here are low voltage, the first one, and then high voltage, the second argument, and third argument is the time delay, and then the next one is rising time, and then falling time, and then the on time, and then the final one, the last one is a period. That's all the argument in the pulse function. Okay. I should have sent you guys all the accounts information yesterday, but I haven't. I'm going to do that right after this class, after I upload the video, right? We'll see you tomorrow if you don't have any other questions.